Okay, let's talk about, this would be section 1.3 in the Zill textbook, chapter 2 in the Sean's outline. We're talking about using mathematical models, using real-world applications and building differential equations out of them. Now, the way this works in the real world is you start with some assumptions, build some mathematical model out of that, usually a differential equation, since that's the kind of model we're talking about here. Solve that DE, check your solutions against real-world data, and if your data don't match what your predictions are, then change your assumptions. And this is a cycle. This keeps going. So here are some of the most basic models that we'll be dealing with, say, this semester, or these make good examples. We're going to look at a few different population growth models. The first population model we might look at is assuming that our rate of change, our derivative of population, the growth rate, is proportional to our current population. The more people you have, the faster your population will grow. That's our model we're building. So when we say proportional to, we mean equals some constant times our current population. So the rate of change of the population is some constant times the current population. Now think about this for a minute. We're going to solve our first DE right now. What kind of function, when you take his derivative, do you get back the original function again with maybe a constant in front? Oh, well, that would be an exponential. The derivative of e to the kt with respect to t would be k times e to the kt. And if we tack on any extra constant in front of that, derivative of a constant, that would just come along for the ride. So this is our solution to that differential equation. We've just now solved our first differential equation. You should check this and check that this is in fact a solution to that DE. And P0 here is just our constant of integration. And we call it P0 because it's our initial population. What's e to the 0? That would be 1. So P of 0 is P0. K here is called the growth factor, sometimes called the growth rate. It's the percentage of your population you grow by per time unit. We're talking population growth here, so we would have a positive growth factor. K would be positive. So, for example, say we were growing by 3% per year, so time is measured in years, and we started with an initial value of 10,000 people. Then we're really solving this initial value problem. K is 3%, 0.03. P of 0 here would be our initial amount, 10,000. So here's our model. Radioactive decay is still exponential growth, only now we will have a negative K value. So it's the same idea. It's just like a population growth model. We assume the amount we have left is proportional to the amount, or the rate of change is proportional to the amount we have. But with radioactive decay, the more you have, the faster it decays. So we still get really the same model. Now we call it A for an amount instead of population, but it's the same model. But we'll have a negative growth factor because we have decay instead of growth. Okay, our next model, we're going to play around with this a few times this semester, is Newton's law of cooling. So this is saying, for example, you take a pie out of the oven. It starts at some temperature T, some T naught, and you place it into a medium, the air, a refrigerator, the freezer, that's at some constant temperature. So Tm here is if we place the pie on the counter in the air, Tm would be the temperature of the air. Then the rate of change of our pi, the rate of change of the temperature, dt dt, is proportional to the difference in temperature between the current temperature of the pi and the air. Okay, we will solve this dE later. This is the solution. T0 here is the initial temperature of the pi. And we get this model that looks like a shifted exponential decay. So we start at some initial temperature and we will decay off, and we don't approach 0, we approach, this says Ts, that's Tm, the temperature of the medium. And here, for different values of K, if we have a bigger value of K, our pi will cool more quickly. K here is actually very complicated. It's related to the surface area of your pi or whatever your object is, the heat capacity of your medium. It's a very complicated formula. We usually find K experimentally. Okay, predator-prey models. We won't do much with these this semester, but they are interesting models. They're just very difficult to solve analytically. So say we've got foxes and rabbits. Foxes hunt rabbits. So if you get too many foxes, they're going to eat off all your rabbits. Your rabbits will decline. Then your foxes don't have any food. They'll decline. Well, if the foxes decline, then the rabbits will rebound because they don't have any predators and they'll come back. Well, now your foxes have more food, so they'll come back. So you get this oscillatory behavior between your predator and the prey. When the prey is increasing, that will cause your predator to start increasing. Until the predator starts to get too big, that will cause a decrease in the prey and so forth. So you get like this lagging oscillatory behavior. So here, this would be a system of differential equations. The population of rabbits, the rate of change of that will equal, well, this is just population growth. The more rabbits you have, the faster they'll grow. But the more foxes you have, you get this negative term in our rate of change, because that would cause a decrease in the number of rabbits. The rate of change would be negative. So we get solution curves that look like this. So this is interesting here. So say we started with this many, what do we have on the bottom? Rabbits versus this many foxes. Then over time, we'll follow along this curve going like this. Prey will decrease, which will increase here. And then they'll both decrease, then they'll both increase, and so forth. We get this cyclic kind of behavior. Okay, last one we'll look at today, mixture problems. So this is a good little problem. You're going to have a group quiz that's very, very similar to this problem. We've got this tank. It initially has 300 gallons of brine in it, saltwater solution. We're going to pour in 2 pounds of salt per gallon at a rate of 3 gallons per minute. So we're pouring in salt water that has a different concentration from what we started with. We're pumping out water at the same rate. For this simplified example, the rate of stuff coming in equals the rate of total stuff going out. We want to figure out how much salt we're going to have at any given time. Okay, so you should pause this, read this, make sure you understand the setup before we move on. Okay, so we're going to let A of t represent the actual amount of salt in pounds that's in our tank at any given time. So A doesn't represent water, it's pounds of salt. Well, the rate of change of A is going to be the amount of salt we're putting in pounds per minute minus the amount of salt we're pumping out in pounds per minute. So we have to do a little dimensional analysis here. Our rate in, we're pumping in 3 gallons per minute of water, salt water, but that water we're pumping in has 2 pounds of salt for each gallon. So our rate in is 6 pounds per minute. We're gaining 6 pounds of salt per minute. How much are we pumping out? Well, we're pumping out 3 gallons per minute of whatever is in there. So our concentration is however much we have at that moment divided by the total, because we're keeping it constant 300 gallons of stuff. So this would be pounds of salt per gallon. That's just how much salt we have in there divided by how much stuff we have. Times our pump out rate is 3 gallons per minute. We're losing A over 100 pounds of salt per minute. It's just 3 divided by 300. So that's R out. So dAdt would be 6 pounds per minute minus A over 100 pounds per minute. Now we're not going to solve the dE here. We were just trying to build a dE. So this is our differential equation. And that's a good place to stop.